You think you know why fire burns? Energy, heat, combustion. But in 1928, Paul Dirac wrote a single equation that quietly shattered every old certainty. It showed that the power behind fire and the whole of reality emerges from hidden quantum rules stranger than anyone imagined. This is how the mathematics of a lone physicist rewrote the laws beneath everything you see. Are you ready to find out just how deep the rabbit hole goes? In the late 1920s, the known laws of physics began to crack under the pressure of new discoveries. The Schrödinger equation, celebrated for explaining the quantum world, began to fail when faced with particles moving near the speed of light. Its second-order time derivatives and lack of Lorentz symmetry led to contradictions, including predictions of negative probabilities and a breakdown of causality. For electrons racing through atoms or crossing cosmic voids, these errors could not be ignored. Paul Dirac, working alone in Cambridge, set out to solve this puzzle. He wanted a wave equation that would respect both quantum mechanics and Einstein's special relativity, something first order in both time and space. The challenge was to find a mathematical structure that would allow the equation to factor neatly, just as the energy-momentum relation for a free particle can be written as a perfect square. In words, the energy squared equals the momentum squared times the speed of light squared plus the mass squared times the speed of light to the fourth. Dirac's breakthrough came from introducing a new kind of algebra. He proposed matrices, now called gamma matrices, that do not commute but instead obey specific anti-commutation rules. This allowed him to linearize the square root relationship at the heart of relativity. The result was a new equation written concisely as I gamma mu partial mu minus m acting on psi equals 0. The wave function psi is not a simple number, but a four-component object called a spinor. Each component encodes deeper properties of the electron. The Dirac equation, published in 1928, satisfied Lorentz symmetry and produced well-behaved probabilities at all speeds. This mathematical leap built the foundation for everything that followed, revealing that the world's most basic particles obey rules far more subtle than anyone had guessed. The Dirac equation did more than unite two branches of physics. It forced open doors no one expected. Inside its four-component spinor structure, the mathematics produced a new quantum property: spin. This was not the spin of a spinning top or a planet. Electrons, according to Dirac's equation, possess spin 1/2, which means the wave function must rotate a full 720 degrees, not just 360, to return to its original state. This was not an add-on or a tweak, but a direct, inescapable result from the algebra itself. The electron's spin, so mysterious in earlier quantum theory, now appeared as a built-in feature woven into the very fabric of relativistic space and time. Yet the equation's logic did not stop there. Alongside the expected positive energy solutions, it predicted a mirror world of negative energies. If left unchecked, these would allow electrons to tumble endlessly downward, losing energy without limit. To prevent this mathematical catastrophe, Dirac proposed that all negative energy states are already filled, forming a vast invisible sea. The Pauli exclusion principle, which forbids two electrons from occupying the same quantum state, would then block any real electron from falling in. This bold hypothesis, a filled continuum of negative energy electrons, was not just a mathematical trick. It was a desperate measure to keep reality from unraveling under the weight of the equation's consequences. The stakes were no longer just theoretical. The equation demanded a new layer of reality, hidden beneath the surface of everything we see. August 1932, California. Inside a dim laboratory at Caltech, Carl Anderson adjusted the magnetic field of his cloud chamber, searching for traces left by cosmic rays. That day, a single photograph captured something no one had seen before, a slender, curling trail bending in the opposite direction from any known electron. Careful measurements revealed its mass matched the electron exactly, but its charge was positive. Anderson repeated the experiment, checking the curvature and ionization again and again. The track was too light to be a proton, too precise to be an accident. The evidence was undeniable. A particle with the mass of an electron, but with a mirror image charge. 4 years after Dirac's equation, the positron stepped out of mathematics and into the world. Anderson published his findings in November, and the cloud chamber image became an icon. The positron's discovery was not just a new particle, it was proof that the universe contains a hidden symmetry, and that equations can predict realities no one had yet imagined. The old picture of a silent, endless sea beneath reality has faded. In modern physics, emptiness is not empty at all. Instead, space is filled with quantum fields, each one stretching everywhere, even in the dark between stars. Particles are not tiny objects darting through a void. They are ripples, brief excitations of these fields, appearing and vanishing with the right jolt of energy. The vacuum itself is restless. Even without real particles present, the uncertainty principle allows fields to fluctuate, spawning virtual particle-antiparticle pairs for fleeting moments. Under powerful electric fields, like those near neutron stars or in high-energy experiments, these pairs can become real. Electrons and positrons can pop into existence, then annihilate in a flash of energy. At the edge of a black hole, the horizon can separate these pairs. One particle is swallowed, the other escapes as Hawking radiation. Every so-called empty region thrums with this invisible activity. The Dirac equation, once a tool for describing electrons, now forms the mathematical backbone of these quantum fields. What was once a desperate fix to avoid catastrophe has become a window into a world where nothingness is alive with possibility. Every spark, every flame obeys equations older than humanity. Reality is not built for our senses. It is written in mathematics. And those rules remain, indifferent and absolute, beneath everything we see.